Welcome to Ask and Learn.
Alright, so here we have that t, our function t is going to be equal to n times t squared evaluated at n over 2. And initial condition t1 is equal to 6. So first we're going to substitute n equals 2 to the power of k. And so this becomes t of 2 to the power of k is going to be equal to 2 to the power of k times t squared at 2 to the power of k over 2, which of course is going to be equal to 2 to the power of k times t squared converted at 2k minus 1. And then we're going to make another substitution here where we let k equal log 2 t 2 to the power of k. And when we do that, we get that this is equal to log 2 to the power of k times t squared 2k minus 1. And we can use some of our log rules. So we get log 2 times 2 to the k plus log 2 times log 2 of t 2 to the k minus 1 squared. Okay, and this is going to be equal to k plus two log 2 t times 2 to the k minus 1 power. And then this is equal to k plus 2 a sub k minus 1. Okay, so that's going to be a lot easier to work with now that we've made those substitutions. And for simplicity, we can really write this as like ak would be an is equal to n plus 2 an minus 1, right? So it'd be in the same form that we're used to. We just have to translate our initial conditions as well. So we would get, so we're going to rewrite to get an is equal to 2 an minus 1 plus n. And then we would have a naught is equal to log 2t to the 2 to the power of 0, right? Which is going to be just 1. So 2 to the power becomes t1, which we know from what we're given is that that is really just 6. Okay, so then we want to find the root characteristic equation here. And when we do that, we get that our homogeneous portion is going to be equal to, right, so we would say r squared is equal to 2. Or sorry, we say r is equal to 2 when we set an equal to r and an minus 1 equal to 1. So it'll be alpha times 2 to the power of n. And then we want to move on to the particular solution. In this case, our function is just equal to n. Which is the same as 1. Multiplying that by 1 to the power of n, and 1 is not a root. So we'll take that form of our particular solution, which would be equal to p1 times n plus p naught times 1 to the power of n, which is just p1 times n plus p naught. And then now we need to solve for this and make sure it satisfies our recurrence relation here. And so we will rewrite it. So we have an equals 2 times an minus 1 plus n. We'll put in our particular solution, p1 times n plus p naught. And for an, we'll put it in for an minus 1 as well. So we get 2 times p1 times n minus 1 plus p naught plus n. We can extend that, so it's going to be 2p1 times n minus 2p1 plus 2p naught plus n. And we can subtract from the left-hand side and the right, so we would get 0 is equal to p1 times n minus 2p1 plus p naught plus n. So we get up the n's and the not n's, we get 0 is equal to p1 plus 1 times n plus negative 2p1 plus p naught. And these coefficients must be equal to 0. So we'll just set them equal to 0 and solve. And when we do that, we have that p1 plus 1 is equal to 0, and negative 2p1 plus p naught is equal to 0. So the first one's pretty easy, right? So here we get that p1 is equal to negative 1. We put negative 1 in here, and we end up with 2 plus p naught is equal to 0. So this means that p naught is equal to negative 2. So we'll put that into our particular solution, right? So our particular solution was looking like p1 times n plus p naught. And so we know this will be negative n minus 2. The entire solution then is going to be our homogeneous portion plus our particular portion. So that is going to be alpha times 2 to the power of n minus n minus 2. So we'll use our initial conditions to evaluate it at n equals 0 and find alpha. And so at n equals 0, we get alpha minus 2, which was equal to a naught was going to be log 2 of 6. Okay, so that means alpha is equal to log 2 of 6 plus 2. So an is going to be log 2 of 6 plus 2 times 2 to the power of n minus n minus 2. Okay, but now we need to put this back into terms of t, right? And so an is really equal to log 2 of t, 2 to the n, but we had called it k previously, so that it is fine either way. So we'll say log 2 t of 2 to the power of k is going to be equal to log 2 6 times 2 to the power of n plus 2 to the n plus 1. So I just, before I had both those multiplied by the to the power of n, and now I've just multiplied out those components. Minus n minus 2. Okay, we can take the exponential of both sides, so we get t 2 to the k is equal to 2 to the power of log 2 of 6 times 2 to the n plus 2 to the n plus 1 minus n minus 2. I suppose we should use these k's. Okay, and when we do that, this is going to be equal to 6 to the power of 2 to the power of k times 2 to the power of 2 to the power of k plus 1 times 2 to the power of negative k times 2 to the power of negative 2. And a little bit of algebra. This is equal to, you can put these below, right? So it'd be 6 to the power of 2 to the power of k times 2 to the power of 2 to the power of k plus 1 over 2 to the power of k times 2 squared. And that is going to be equal to 6 to the power of 2 to the power of k times 4 to the power of 2 to the power of k over 4 times 2 to the power of k. Looks like up here I forgot a 2 to the power of 2. So it's definitely messy. So at the moment we have t 2 to the power of k being equal to 6 to the power of 2 to the power of k times 4 to the power of 2 to the power of k over 4 times 2 to the power of k. All right, so now if we let n be equal to 2 to the power of k, so that was our first substitution we made, we end up with t to the power t of n, which is equal to what we have up here. We get 6n times 4 to the power of n over 4 times n, which will simplify as 6n times 4 to the power of n minus 1 over n.